at a hospital, so this already starts off good. I was told right out of the gate, first thing in the day, the lady in this room, she's like, she does not like males. She will be just hateful and rude all day long. And from the second I walked in the door, I mean anything. And after like, I'm on hour 8 of this and got 4 more to go or something, eventually I was just like, look, I have done nothing to you all day. I'm doing nothing but trying to help you. You will not continue to speak to me this way.
Wow.
And she, of course, threw a fit, as I expected. And then when I left, I found out, after the entire day, I chose that moment, which was probably like 10, 15 minutes after the doctor was in. It's like, really, the only thing we should do is conduct hospice care. I was like, oh, I put up with her all day until this moment. And that's the moment I chose.
Yeah.
It's like, oh.
It's just really pouring salt on it, right?
Yeah. She was one of the most hateful women I have ever seen in my life. She really was. Wow. People, not
I'm sure you see a lot of different types of people in the hospital.
Yeah, but you know, the really messed up thing, I saw way more hateful and unreasonable people working in restaurants than I ever did in a hospital.
Somehow that doesn't surprise me.
I'm like, this is your health, and you're just like laid back and go with the flow, but God, if your potato's not fluffy, you know, like, it was I was like, I feel like I'd be more concerned with my health.
You would think.
But no.
Most people, that what you're talking about is just a projection of everything else. And in their health, they're just like, let me just get out of here as quick as possible. I'll say anything to not have to think about this another second.
Maybe. Done much on homework too yet?
Brought it.
Brought it?
I have
You
scrap.
brought yours too?
I have blank paper for it. Those are big steps for me.
I had that much of it.
Hey, Kyle's ahead. When he was talking about getting
I
caught
wrote
up,
my name on it.
dang it! I guess I'm in last place over here.
You still got,
Okay.
you know,
Well, I'll see
3/4
if
of the class to come in. You might be.
I think, Doctor, you would be mad if I started working on my homework while she's lecturing.
Or whatever.
Say again?
Negative.
They said that they're ahead of me on getting started on the
Hang on,
homework.
this is not what we said. I said, have you all started on the homework? And all of a sudden you make it sound like I'm sitting here bashing you.
You can talk together, and sometimes he actually usually start earlier, right? Then you both.
It depends on the week.
Oh, okay, this
Depends
week
on-
is not busy, then you can.
Yeah. And I had to be fair, I had an advantage the previous week because of the qualifiers. Since I was already
yeah, then
done.
after that, you
So-
give the same food now.
No unfair
No,
advantage for
any,
me.
yeah, okay.
So I actually,
Zane, I
can I
just
ask
did
a
homework.
question or two on the first problem, because I haven't made it far, but on the first problem, are we saying
Oh,
that
no, only homework.
the way function is only
I
a
haven't
function
started
of
yet.
R?
Yeah, this
Uh,
normalization constant is just for
Yeah.
first part or what?
Page 387.
This normalization constant is for both part or just first part. Yeah.
6.9.
This one, right?
Yeah.
Okay, this be the vector, right? So R, say
Okay, that's what I, that's,
Last
It might be reading.
because I think this is a hygiene item, so you know
Yes.
the function.
Oh,
okay.
That's the only question?
Yeah, yeah, I,
See,
Okay.
correct.
Yeah.
Only that.
Yeah.
Yeah.
So I started thinking that, and then I'm like, no,
Yeah.
because
Yeah.
it's,
I think there is, the other also deal with the hygiene item.
Dr. Yu,
Yes,
this normalization constant is just for part first term or whole part?
this, only for this one.
Only for first term?
Yeah, yeah,
Okay,
yeah, for first one.
thank you.
Okay.
How long did you work at the hospital for?
for probably 2.5 years.
Oh, yeah. Are you meeting in the same room?
Morton Brownsboro. It's a pretty good hospital, actually.
Oh, okay.
They just opened a new Orton's on Buffalo Road.
Hospital or? No, because Audubon's already over there. Yeah,
Yeah, but they
daycare or something,
just
yeah.
opened a new one. It's like right by the Panera Bread and Qdoba.
Okay. No, that's not far from the main hospital then.
You all joined us at the
I know.
big table today.
Yeah.
It's nice.
Yeah.
Yeah, we're ready to have a conversation.
Yeah.
Let's start it. We have 5 minutes past. All right, let's just try to remember. We discussed the rotation operator and we prove for any finite angle of a gamma about this n direction of axis. So that is the operator R n vector of rotate about the gamma angle. That is exponential here. This angular momentum that is generated, right? Generator of this operator. Then next question we ask ourselves, okay, this is a arbitrary axis. Can we represent this any rotation operator about the arbitrary axis by a fixed, like this x, y, z, a fixed coordinate, kind of a series of this consecutive rotation about this x the coordinates? The answer is yes. That is the Euler rotation we're going to discuss today. This is homework 2 I also put in, and your homework 1. Okay, you okay, Pedro? Yeah. Good. All right. So then what he said is like this. Okay, that is arbitrary, right? So first we want to rotate the z-axis. We try to rotate the z-axis parallel to the n and rotate about this unit axis. So how to do that? First, rotate about the z-axis with alpha such that this x prime, the x prime n and z prime, because z prime equal to z, since about z-axis, right? They form the same plane. That means this became a same plane. So the y prime is perpendicular to this plane. That is the goal. Right, so we try to rotate by alpha again, how much it is, you just depend on this n vertex, right? And then now we have a y prime. So now second step is about y prime, the axis, rotate by beta angle, such that the z prime, same direction is n, so that is z double prime. So now we first rotate to here, and then rotate the z, come to here, about the y prime. And now we have a new the coordinates or axis, the double prime, and about the double prime, we just rotate this gamma. So that is to follow this property of the rotation operator. Any product of a series of rotation operators still give another rotation operator, right? So that means any rotation operator also can be composed as a series of consecutive several rotation operators. So now let's the first one is about the z-axis, right? Rotate about z-axis angle alpha. Then after that, rotate about y prime with beta. And after that, we come to here. So now we perform 3 rotation replaced by this one, right? That is gamma z double prime. Okay. So you see, this means we can perform 3 individual or separate the rotation, and that can replace any rotation about any arbitrary axis. Okay, now this seems okay. However, you see the y prime and z double prime, they are not in the fixed coordinates. We want to rewrite this again, and finally, they only replaced by this rotation for around x-axis, y-axis, or z-axis, not y prime, not z double prime, right? So now, next job, right? This is not inconvenient, still inconvenient, even though we can separate into several axes. So then what we have to do is how to deal with this such that we can replace y prime by y or with z and z double prime by y or z. That is okay, so now let's think about this. First, the y prime, how to get the y prime, is rotate about the z-axis, right? So that is to perform rotation about z-axis, we got y prime. So now, let's consider, first, let's each individual, right? So remember, each individual is follow this, right? So about z, rotation about z-axis with alpha angle that is exponential minus I divided by z, right? Then about the y prime is beta angle, exponential beta y prime. About z double prime gamma is exponential I gamma. So here again, they are not in the same coordinates, so that's why we are going to replace. Now, how to replace the first one? Okay, right? This is about the how to replace this one in terms of this x or y or z axis. So because you see here, this is a function of gy prime. So we know any operator a function of another operator, then any behavior of this operator should be or dominated by the function of the variable, which is operated by that, right? So because gy prime is how to get it, this operator, right? By the operator of the rotation, we know the operator after rotation has this relation, right? It's about the r and the gy, right? Okay, r inverse. So that is the beginning of the discuss how the wave function rotate and under rotation, how the operator under rotation, right? This is a relation. Y to y prime is acted by this operated by this operator r z hat, right? This gamma. So now that's this one. And remember the property, the inverse is not about the electric, right? Okay, because that's so, then it is a function of gy prime. So if gy prime follow this, the function of gy prime, the ry prime should be yeah, speed for the same thing, right? So the R y prime beta should be same thing like this. The operation about the z-axis with angle alpha from the y to y prime, right? You have question? Okay. So that is why y prime. Now once we have this, since we need think about this, so let's first consider if R y prime beta is like this, then how about this inverse? Is we take this inverse, right? Let me take this inverse first. So we know the product of inverse is equal to the inverse of product equal to the product of inverse, but the position change. So that this one is R Z inverse, so it becomes self, right? And the second one, this one, inverse, and this one, inverse, right? That makes sense? Remember this operator in chapter 2, right? So now, you can write further. So first one I keep here, and the R inverse, the R and the Y inverse, so that is minus beta, right? R1 minus beta, and then the RZ minus beta. Okay, we are going to use this one and this one in the next step. That is for RY prime. How about RZ double prime? The double prime, similar, that is rotation about the y prime axis, right? Rotated by about this, by about the gamma, beta, right? So here, this z double prime is from z prime to here. How to make it? We rotate about y prime by angle beta, right? So here, let's first, because this one is, I already written here minus gamma and tau. Double prime. And here, consider this. So because GZ double prime is what happened R about the y prime beta. But here, this is a z prime, right? Not z. Right. Here we do the rotation about z, got z prime, even though z equal to z prime, but this is z prime. And then we perform the second rotation about y prime with the angle beta, right? So that is z prime here. Okay, so because this and then here, these two is here, right? We already obtained. So then you can have this, it is here, R, Z, alpha, and R, Y, beta, R, Z minus alpha. This one is the first, is this one, and then GZ prime, right? Okay, GZ prime, let me see if I want to replace right now here. Okay, here we can also do that. What is GZ prime? Is about Z alpha, GZ, right? Okay. So this is a GZ prime, and then R y prime inverse, so that is this one, right? Z alpha R y minus beta. And Z minus alpha. So that is the GZ double prime, and similarly, the R Z Z double prime, notate about the Z double prime of an angle gamma, that be R about Y prime, notate beta, and from about Z prime, gamma, and then Y prime beta inverse. Same thing like this, right? Then each individual here, so this one, so that is R, Z, alpha, and R, Y, beta, R, Z minus alpha. That is the first term, R by prime beta. Then R, Z prime gamma is R like this, right? R, Z, alpha, R, Z, gamma, yeah, and R, yes, R, Z, inverse, okay. I think it's just immediately use minus here, right? Minus alpha. So that is second of RZ prime, and then the last one, RY prime inverse, is this RZ alpha, RY beta, minus beta, RZ minus alpha. That is the third one. Okay. Now let's try to see if we can, some terms is equal to, so this one equal to identity, right? These two. And this two, right? So that's equal to, the remaining is R, Z, alpha. Okay. R, Y, beta. So this became R, Z, gamma. And this becomes R, Y, minus beta, Z minus alpha. This is the RZ prime, double prime, this Y prime. Now we substitute those two here. So we are going to find the final, okay, define this is R as a function, three angles. Usually we use, that is so-called this Euler notation. Use this notation means we have three rotation together. Okay, so now, this is not enough, but then I'm going to go back. So here now come back to here. R, then is equal to the double prime gamma. And beta and RZ alpha is equal to, now I'm going to substitute the double prime here. We have 1, 2, 3, 5 terms, right? So keep it Z alpha, R, beta, Z gamma, minus beta, Z minus alpha. The next one is this one, right? R by prime, which is R, Z alpha, Y beta, Z minus alpha, right? And this one. Now again, we can find here, this one is unity operator, right? And then when this is unity operator, you can see these two. Also unity operator, right? So, any others?
First and the last.
Sorry,
First one and the last one.
the last one.
And the first one.
No, we cannot move. Let me think. I missed some terms here. Oh, okay. This is R double Z prime, Z double RY, but I forgot this one. Right? So here, yes, you're right. This is Same thing. Okay, so these two also unit operator, so then the remaining you can see only these three. Right, so now this is good. So finally we have Z, half, Y, beta, Z, gamma. All are only along the fixed axis Z and Y. Okay. So now come back here. That is written in terms of this. So now we have Z alpha, and you can see the order is also fine. Alpha and Y beta and Z gamma. Now each term is here, like this exponential, right? So now we can write down exponential minus I alpha or h bar gz, exponential minus I beta or h bar gy, and exponential minus I gamma or h bar g. But we cannot change the position since gy gz does not commute each other, do not commute, right? Let's keep here. And how about this inverse? Is inverse of gamma, and that inverse is okay. So the inverse is here, right? R alpha beta gamma inverse, and it's equal to R Z alpha Y beta Z gamma inverse. Inverse of the product equal to the product inverse, right? So that is RZ inverse gamma. Y inverse beta and Z inverse gamma, right? And the inverse we know is a negative, right? So Z minus gamma. Y minus beta Z minus gamma. You see the position change, right? Not only change the from positive to negative, but this position is to right hand side and left hand side will change the position. That's be careful when we take the inverse. Okay, so we have the operator, and we know how to represent the operators. And anytime give us the arbitrary angle, then you know arbitrary axis, so you can know project on the xy plane, so you know where is alpha, right? And you know beta. So very easily you can form this, right? That is alpha, beta is nothing but this axis project to xy and the angle between the z-axis. All right, so next, this is like Dirac notation, kind of Dirac notation. That is arbitrary expression operator. Now we want to represent in the either matrix representation or position representation. So how to represent, to find this the expression of this rotation operator in the matrix as the first. When we say we want to represent in the matrix representation, you need to find the which space, right? You need to find which space and how much dimension of the space such that you can represent or project this one into that space, right? So which one we are going to select? You think, okay, you think here, the rotation operator is related to the angular momentum. So it is easier to say or select the space which is eigenstates of angular momentum, right? So that is the, we are going to select basis, right? Select this, because we know if this basis vector is eigenstates of the angular momentum, then when angular momentum apply that states give an eigenvalues. And same thing for the function of this operator, right? So that is we are going to select from here. All right, so if you select here, now let's first know the relation, then we can apply. So now let's look at this one. I just let me first write down here this again. Yes, in terms of exponential, well, this angle, this is a z, right? And another one is gy, gz. So, commute. G square commute with GZ, GX, GY, right? Because chapter 5, the square of angular momentum always commute with its components, right? So then this function of components should be also, right? Immediately got this. So we got this means what? Commute means G square multiply R hat equal to R hat multiply. The position doesn't matter, right? So then look here. G square apply this state which is after rotation. So I'm going to so this is eigenstates of G square. Then I'm going to make a rotation on the states. So give a new state, right? So we're going to see this new state still the eigenstate of G square or not. So we are going to look at this step. Because they commute, right? So I can change the position. Alpha, beta, gamma, G square, Gm, right? Since they commute. Then now Gm is this cat is of eigenstates of G square. So how much? H bar square G plus 1, right? This eigenvalue G square apply. And then so what does it mean? You see this one, if you consider this another cat, and G square apply this cat equal to this constant, which is eigenvalue of G square, multiply this cat again, right? So what does it mean? So even though this the eigenstate of G square after rotation, it still belongs to this one of the eigenstates. And here with fixed, the G doesn't change, right? G is still G, but different N. Right? So what happened is in this how much this space formed by given G is 2G plus 1, right? In the subspace. In 2G plus 1, we have 2G plus 1 Gm eigenvectors, and then one of the eigenvectors after the rotation will go to another one. But still within this one. So G is same, but M different value. So what that means, this operator, we can rotate, use this operator to rotate this eigenvectors of the G square over this eigenvector over this basis after rotation still within basic, not out of the space, right? So that's good. If that case, okay, now we are going to consider how to represent. So now let's look at this one. Alright. Comma. Let's look at this one, right? I'm going to insert I in front of the R rotation operator because the I will not change, right? So that is in chapter 2, we always try to perform this. So now this is completeness, right? So I equal to M summation from minus J to J, or M prime, J M prime, J M prime, right? That is I. Okay. So now you can see this one is the rotation operator sandwiched by these two states. So that is a scalar, right? Matrix element. Okay. Now I'm going to rewrite this one. This one I'm going to use. It is dependent on J, and the index is this bra is M prime, and cat is F, right? I'm going to use D for giving angles. Then this is operator. Then when the operator apply this is given, this is a matrix, right? This is a matrix element. And this matrix element represents this matrix representation of this rotation operator, right? So here, let's give a big, since I go here, so now what is the matrix element? That is the inner product of this rotation operator within this eigenstates of J squared or Jz, right? So that we called, this we called Wegener function, which matrix element. Then this from the matrix D, which is matrix representation of rotation operator in here, right? 2 by 2j plus 1, 2j plus 1 matrix, since this m value start from minus j to plus j. So now here we have m prime value in the column here, and m value go to here. The first one, j, dj, and m prime and j is we start from maximum value. The next one is dj, so j prime still j and j minus 1 until finally j minus j. And then they go to row. So here the second one, the second row here is j minus 1, j, right? And then finally e minus j, j. J minus j minus j. So we call this matrix Wegener matrix. So Wegener matrix is nothing but is a matrix representation of rotation operator. That is what I need, right? Because here J is a general angular momentum operator. It may be the orbital angular momentum, may be spin, maybe the addition of 2. So that is very general. Now let's look at the R is here, right? This rotation operator actually is product of 3. And here, this eigenstates is also eigenstate of Jz. So if you go to the detail, you will see this Wigner function or matrix element can be written in more details. It is here. D, J, M, and prime alpha, beta, gamma is J m prime exponential minus I alpha upon J Z minus I beta J y gamma J Z, right? So Jz, it is eigenstates of Jz, right? This is also eigenstates of Jz. So what we have? What we have is h bar m prime, right? Exponential minus I alpha h bar and then h bar m prime. No Jz, that Jz become because this eigenstates of, and it is also Hermite eigenvector, right? So that operator. So here, then yes, and I keep here this one still here. This is Gy, not eigenstate. So this one exponential minus I gamma. So here this is a h bar m, right? Then I can, because this already I can take outside, right? Because this is function, is numbers now. So I take outside exponential minus I h bar, h bar cancel, right? Minus I, so h bar, so m prime alpha plus m gamma. Yes. And then now I'm going to, okay, let me write that in. So just define. I'm going to read it. So now I'm going to lower d, j, m prime, m, but now this only depends on angle beta. So the lower d, j, this is matrix, another matrix element, which is the exponential minus beta over h bar gy. This one we call Wigner formula. Then, even though this is a capital, the Wigner matrix actually, this becomes simple. So depending on alpha and gamma angle is simple, just count this quantum number. But then the matrix is down to only the Gy, exponential of Gy. So for this one, we have a general formula, because we have a formula how to calculate this one, since we know y is not, this Gm is not the eigenstate y, right? So we need to replace y, Gy in terms of J plus minus, and you know J plus minus apply this case. So that details we will not go, I just gave you the formula. Is, okay, this one is equal to, what you need to do next is just substitute the given numbers, J and M prime M, right? So then that's enough. So here it is J plus M factorial, J minus M factorial, and J plus M prime factorial, J minus M prime factorial. Then we have a summation for K. The inside K is minus 1 to this power is K plus M prime minus M. And if there's a cosine half beta, its power is 2J plus M minus M prime minus 2K. And the sine half beta power is M prime minus M plus 2K. And denominator we have J minus M prime plus minus K factorial, J plus M minus K factorial. Then there's K plus M y minus m factorial k factorial. Here. How to determine k? So the k is all, let me say this way. All integer number. Okay, then J has a half. Wait, K is over all numbers that none of the argument, none of the argument in the denominator has negative, so that is so we have four terms, right? Four denominator in the four factorial. Factorial. Okay. So that means we have a four factorial, and we are going to select k such that each of them there's no any negative. If there's a one term negative, that k is not allowed. It's forbidden. So how to understand this? Let me play one example so that you know what this means. And later you can do for any case, right? So let's say examples. J equal to 1 and n prime to n equal to 1. Let's select this simple case, right? So now we are going to find is 1, 1, 1, right? Okay. D, J, n prime m. 1, 1, 1 means any angle beta. Then let's follow this formula here so that the first J plus n, that is 1 plus 1 factorial, 1 minus 1 factorial, 1 plus 1 factorial, 1 minus 1 factorial. That is the first here, J plus n, J minus n, J plus n, 1, J minus n. Multiply, right? So now k, we do not know how much k, but let's write down here first, see how many the k allowed for this non-negative argument here, so that is minus 1, k plus 1, right? M plus 1, minus 1. Cosine beta half. So here we have 2 multiplied 1, j is 1, plus 1 minus 1, minus 2k. Sine half beta is 1 minus 1 plus 2k. Then denominator here. 1 minus 1 minus k factorial. 1 plus 1 minus k factorial. K plus 1 minus 1 factorial k factorial. So now let's see. First, this is a minus k, right? Factorial. This is a 2 minus k factorial. So this is a k factorial, k factorial. If they ask the argument not equal to a negative, so k should be negative, right? From here. This one, k should be smaller than 2, right? Or equal to 2. This one, k should be larger or equal to 0, right? So combine those together, which value? K should be negative from here. K should be positive, so only 1, 0. And 0 satisfies this one, right? So k can only select 0. Therefore, the summation here, it became only k equal to, there's no any other summation, right? So that is analyzed here. Now I'm going to continue. So here, this one is 2 factorial 0 factorial 2 factorial 0 factorial. Summation is no, so that is minus 1, k to 0, right? So that is 0. This one, 1 minus 1 is 0, and k is 0, so that is 0. And cotangent half beta, which is this is 2, 3, 2, and 0, right? So that is 2, right? This is 0, this cancels, right? That is 2, 2 multiplied 1. This one, 0, this cancels to 0, right? And the denominator here. So denominator takes 0 factorial, 2 factorial, 0 factorial, 0 factorial. Okay. Here that is 1, right? So now we have this one 2 factorial, we have 2 factorials, so that cancelled, right? Yes, so fine, I'll do something. Yeah. Okay, so that cancels. And then this one is 1, so now we have only cosine square of beta, which is 2 plus cosine beta. So this is a way how to calculate this Wigner formula by this expression. If asked to do some others, you can follow the same thing and get this result. Okay. That is for details. When we know the Wigner formula, we can calculate the Wigner function, right? Since this one is simple. Just explanation.
Dr. Yu,
Yes.
what is this in parentheses telling us? The k less than or equal to 0,
Yes,
k less than or equal to 2.
That's from this analysis, right? Because this is minus k is here, right? This one equal to this. So if asked the non-negative argument, k only can have negative.
Right.
So less than equal to 0. Any other question? That's only, right?
Yeah.
Okay. So now, let's go to discuss some, probably introduce this Wigner matrix, Wigner function, and Wigner formula. So let's discuss some of the properties, which is important. Properties of the functions. The first one. The detailed proof is very easy, so if you are interested, you can prove yourself. First, we already proved that this is a J square multiplied with G, this Wigner function. It's nothing but this eigenvalue of J square multiplied itself, because we commute each other, right? We have already proved that. So this one is simple. Similarly, for this GZ, since it's also eigenstates of GZ, this product is also operator apply this Wigner function is equal to this eigenvalue of this operator multiply. Because these two are these eigenstates, but this one, if you can prove yourself, if J plus minus multiply or apply to this Wigner function, since we know J plus minus is not Jm is not eigenstate of this, but we know it's a plus raising and lowering, right? So I give you the result is J plus minus n prime, J minus plus n prime plus 1, and the J here, but here, n prime minus plus 1, yeah. I leave this just on the same time, so leave this proof yourself. If you have any question, let me know, we can go together. Second one, is, like look this, this matrix is a complex function, so it is a diagonal or complex conjugate is not equal to itself. So now let's look this one, EJ m prime m. How about this complex conjugate? It is equal to, very easily, so because the definition is this one, right? Then we know if we have this, take the product of this CAD and this operator, its dagger is equal to CAD go to bra and the operator go to this dagger, right? So that is GM, this CAD became bra, and this go to R dagger, and GM prime became CAD. Then R dagger, we know that is minus, right? R negative alpha, negative beta, negative gamma. So, very easily, it is still another Wigner function, which is, but now you see this, the first m prime m, right? The row is m and the column is m, but now it just changed order. So m became a row, m prime, and then angle O became negative from positive. So that is the relation between the complex conjugate with origin. That is a property, the property of this Wigner function. Number 3 is it's orthogonal over unitary, so that's given this one, and proof that is also very easy. So here we have a D, J, K, and alpha, beta, gamma. It's complex conjugate of itself, but here is a K prime and alpha, beta, gamma. So here, this row, the row has a different value. So this matrix element, somewhere old m, here m, column the same, right? That gave us delta k prime. So when k equal to k prime, that means this is the same matrix element. They are all same. Then it's a diagram multiply self equals 1. So when if k prime equal to k, we immediately have this summation for OM, EJM, KM, alpha, beta, gamma, EJKM, alpha, beta, gamma equal to 1. Similarly, this one is very easy. You can prove. You just substitute these two D functions by this definition here, and then you can see this orthogonal of these eigenvectors. Very easily you can prove yourself. Similarly, for this is a summation for n. Another summation for this is for the column, and for the row for column do the same thing. So you have m k. Different column, then they are orthogonal, but if same, then we got sum of O. Properties of this Wigner formula. This one, if in homework, let's go to homework 3 maybe. I'm going to see if they have some other important problem, they will not do this, but if yes, I'm going to answer proof. So here, the first one is if the angle is pi, if beta is pi, that is equal to -1 g minus m delta M prime minus M, or minus 1 to G plus M prime delta M prime minus M. Second one, if no rotation, that is angle 0, that is delta. Third one, we have the angle is beta. It is related to the angle, positive angle, and the negative angle is you just exchange M prime with M, and then the angle go to this. I think this is really like this. It's equal to the inverse. This is sometimes we use, sometimes not always use this. All right, so that is the matrix representation. We find that this rotation operator can be represented by the D matrix or D function or a Wigner function or Wigner matrix formula. Now, how about this? If the J is optical angular momentum, so that means we can represent this. We know the optical angular momentum, the eigenstates in the position representation, spherical harmonic, right? The spherical harmonic, if we use try to find the relation between this rotation operator and spherical harmonic, that is if J is angular momentum. So that Jm will go to Lm, and then in the position representation, there's a relation. That's a spherical harmonic, right? So we are going to find the relation between this and D, instead of G now is L, N prime N, alpha, beta, gamma. This is some of our important relation. So now let's just briefly discuss this. Here, I already write down here, right? So now that is spherical harmonic, that is on eigenvectors of L, the optical angular momentum, project to, or in this position representation, right? So now let's consider if the R prime is this after rotation, that is we look this. We know in the position representation, this is the basis. So the operator, rotation operator applied is give another one, right? So R prime. So that is the relation. Now let's look at this. If this R prime is after rotation, then we get this. In the R prime, after rotation, we have another side of this basis vector. Then we are going to project. So R prime, LM. Let's look at this one. That is the angular eigenvalue of eigenvector of the optical angular momentum project to R prime. This R prime is what happened is rotation operator applied to this, right? Let's look at this conjugate. You may say why it starts from here. Then that is the direct relation to for this one. Then if we take the original is with this conjugate. So now let's look at this one. So this one is definition we know is project to the R prime, LM. Okay. Then just rotate, right? The change, bra become cat bra. Then I'm going to insert, since R prime is this one, right? So that is LM R at the rotation operator applied R. Now I'm going to again use the identity operator between this one and this one and this one. So now this is the reason why I'm going to do that, because I'm going to replace this one by a matrix operator, matrix element, right? So here this is operator applied. So if I multiply I, so they have a summation of all these eigenvectors. Let me just write this up here and then we can go to next step. So R alpha beta gamma summation. This one, since this sum of this eigenvector form this completeness, right? So we know that is sum for m from minus L to L, right? And L m prime, since to distinguish m prime L m prime R. Okay. Now I move this inside the summation and prime from minus L to L. And you can see here, this one and this. Right? This is the operator R and sandwiched by this L and Lm and Lm prime. So that is the matrix element of L, but here row is M, column is M prime, right? And here this one right? This is just complex conjugate. So I have to start here. All right, so now what is this one? I think I need just one. This one is L M star theta prime phi prime, right? After rotation. So this is R prime. So here, like I said, this inner product is nothing but this spherical harmonic function, complex conjugate spherical harmonic complex. This is M prime. No M prime. So this is M prime. So, but after rotation, so this angle is theta prime, phi prime. That equal to summation all this matrix, which is a D matrix, multiply spherical harmonic before rotation. But this index M is from M prime sum all, right? Okay, so that is the relation. I'm going to say equation 1. Now I'm going. This is for the star, right? So now for this Y L M theta prime, phi prime, which is right, is this one. And here, this one, you can do this, take the complex conjugate, right? So that is R, but here is R complex conjugate, right? Remember, when I take this inverse, so that is R beta gamma. Now I'm going to insert this R here between this one. So now I have a summation M prime from minus L to L, and this is R L M prime R hat alpha beta gamma L. So this one is a spherical harmonic, but not star, right, itself. And that one M prime from minus L to L. And then this one is D L. Now this M prime, M. Sorry, here. But now we know this conjugate because the unitary operator is minus inverse, right? That is minus alpha, minus beta, minus gamma, and yeah, and this one is Y L n prime theta y. That is equation 2. Okay, maybe since let's use a complete conjugate since we later use this. B L n prime n prime theta gamma conjugate. This is a general. Now we can select the particular case because R is arbitrary. So, because this R is arbitrary, why not we select R just along the z-axis? So, example, if we select this R and theta equal to 0, so that means R is parallel to the z-axis. Here, X, Y, Z. Here is my R. So if I select this R, then here, theta is 0, right? Because R is theta is Z, angle between Z and R, so theta is 0 case. So for this case, let's look this one, right? And this is for particular case, with theta equal to 0, so we have y L m 0 phi m prime. L phi is in chapter 5, we have this L minus m prime factorial, L plus m prime factorial, and exponential I m prime phi p m prime L. When theta equal to 0, so this is a 1. This one we have a value is equal to and only m prime equal to 0. So that is L minus m prime factorial L plus m prime factorial exponential m prime 0. We have this. And similarly, we take this complete conjugate, L prime, sorry, this is 0, 0, 5. Is, I just take the complete conjugate, only it's here, right? Take this minus, the others are same. Plus m prime factorial exponential minus I m prime 5 delta. Okay, when we have this, so now let's look this one. So y star L L n, right? L n, this one. Set apply. After rotation, this is spherical harmonic. How to change from the before rotation, after rotation. That's due to this rotation operator, which is Wigner matrix. So that is we have that. Now, summation for all the m prime, right? And d l m prime alpha beta gamma, right? And that one I have just put here. So that is square 2 L plus 1 over 4 pi L minus m prime factorial L plus m prime factorial exponential minus I m prime phi delta m prime 0. So this summation for m prime, only m prime to 0. Then we have a d L m 0. M and this cancel, right? So this 0 is 1. So that is So now we have a relation between this Wigner matrix and this spherical harmonic. Therefore, for all these columns 0, this matrix element are not equal to this constant multiplied the spherical harmonic L n to the 1. Similarly, from the equation 2, I do the same, so I just give the result. That is, so from equation 1, we have from equation 2, let's just give the final result. I think that is quite easy. So that is. Its complex conjugate be 0, gamma. It's this one, right? Because here, this operator, so we take this one, that is, take this complex conjugate, that be LM, oh yes, LM, right? Right, take the reverse, then that is, so M prime, so that is find the same thing. Here, this is M prime 0 equal to 4 pi over 2 L plus 1 Ln. Okay, so we have these two equations, two relations between this. Then you can go further. So now, you see here, let's see, R, this corresponds to the R, the rotation operator applied to the vector R, right? So that is rotation about Z, alpha, and Y, beta, and Z, gamma, right? Now let's look. So rotation of this is gamma. So first, rotation R about the z-axis with gamma, they still go to R, right? So that is R prime still R. You agree? Let's look at this one. This means I rotate R about the z-axis with a gamma angle. So R is about the x. Whatever you rotate, still R, right? So then next, so next, y beta R. Now, y, so about this y, right? About y, rotate about y with beta. So now, go to R prime, right? So the R prime is beta. This is beta. Now that is and then now this one still again about z with alpha, right? So that is how much? Right? Okay, so now that is you go to maybe go to here. Double prime, right? That is what happened. Now you can see this is okay. That this one I use R prime actually corresponds to R double prime. So maybe to I don't want to make this confused. Let's say this one R1. So this is R2. R2 equal to R prime. That makes sense? Okay, so here, let me see, R1, sorry, this is R1, R2, sorry, this is, no, this is R, this is R1, R2 equal to R prime. So what does it mean? Theta prime, phi prime is the angle of R prime between angle R prime to Z axis theta prime, right? So this angle is beta. How about this project to the xy prime, that is phi prime is be alpha, right? Okay, no, I think this one is not. Say alpha and then go to here, right? That is alpha. Okay. Yeah, after the project to here with the Z, this, and then we rotate this R, this new one. Okay, that may be just so if I don't about this Z and if I about Y, if you rotate here, then this is a 1, and then rotate this one, you may not get confused. So if this one, I'm not sure. But let me just, do you agree? Okay. So here, because when you rotate about Y, you still either this one, this angle beta, and then you do this again, you take about this Z again, so you have project to here, right? Or you project to here, this is so what this means now from here, then we have two equations about this relation D, this one, right? D L M0. Now alpha beta gamma is equal to 4 pi over 2L plus 1. Yeah, okay. Y L M. Now theta prime is beta and phi prime is gamma. And that's true. Right? So that is this one. Okay, this is a case. This is I write up here somewhere. Over there, right? So okay. This is the first one. So that is the first one is this one and come to here. Second one is this one, so that is the DL M0 alpha beta gamma. It's conjugate equal to 4 pi 2L plus 1 by L M So that means for those matrix or function, the function we can use a spherical harmonic to find, since we know the solution of this. And of course, this is when the angular momentum is alpha angular momentum. Oh, sorry. You have another class, right? Yes. Sorry, I saw you have time. All right, let's stop here. You have question? You listen? Okay, all right. Yes, more homework. you think you cannot finish homework on Wednesday, you're okay if you postpone. I'm okay. The next Monday is